Good evening. This will be part 4 of the idle speed control system and the idle speed air valve adjustment and how you actually adjust it. Today we want to talk about this. What we need to adjust, how far we need to adjust it, where the actual issues are in terms of that they're getting sticky, and to what current to adjust this. This is a PDF I made, and I will post this PDF to a Dropbox link where you can download this for reference, and you can look at this then at home and you can see it better and study it. It will be underneath this video, in that above the video, or below the video and above the comment section. It's basically the description of the video where that is going to be, and this may be the most important video you have ever watched if it comes to idle speed issues on 560 Mercedes-Benz and 420s, and it may apply to other Mercedes-Benz models as well. With that being said, this is going to be a rather long video. I would think probably at least in the 15 to 20 minute range, because there's a lot of things need to be talked and addressed. And so what you may want to do is you may want to get comfortable. You may want to hit the pause button and go to the refrigerator, get yourself a cold beverage, maybe some pretzels or something to snack on, to munch on, and then wait until the wife went to sleep and the kids are in bed, and then you take a look at this video when there's no one there who can disturb you. I will put the myth to rest with these idle speed air valves, how they work, how they're adjusted, and whether or not it makes any difference of what numbers you got on here. I did some experimenting this week, and I went into the last nook and cranny in this system, and I can tell you now exactly of what you need to do, where the pitfalls are, and how you can determine whether or not your air valve is still salvageable or not. With that being said, there's a few requirements. You have to make absolutely sure before you even start doing this here that you have absolutely no vacuum leaks. If you have watched my other videos, I got the playlist in there with the big repair, where I went in and I redid all the seals for the intake manifold system. Do yourself a favor, if you haven't done it yet and you have time, do it. It will be worth it, because that rubber stuff dries out. And as to the two gaskets which are between the upper intake manifold and your heads, the left head and the right head, is get the Mercedes-Benz gaskets. They're $12 or $14 a piece. You're looking at $30. But they have the correct silicone already on the gasket you need, because there's water going through there. And the aftermarket ones and the cheaper ones don't have the right silicone. They also have the matching holes for these little guide pins which are on there, so the gaskets won't shift. That is something. Make sure that your vacuum is fixed. Every vacuum on this car has to be 100% right, because none of this stuff here makes any difference. Air injector seats, the seal of the fuel distributor to the airflow or mass divider air mixture plate unit, Luftmengenmischer is the German name for that. That's the unit below it. Make sure that the gasket for your throttle is good, and that the throttle switch is adjusted correctly. That's in that video too, the big repair on how to adjust that. Otherwise this will not work either. And yeah, all your vacuum hoses basically at that point. The brake booster, that the brake booster is not leaking, and that the check valve in the brake booster vacuum line is also working correctly. Once that is all taken care of and you got idle issues, this is now the point where we are. And as most of you know, one of the most searched topics is the issue. Let me close this here and this here. We don't need this. This is what we want to focus on. And like I said, this PDF will be available. The internal, this is basically the picture as we look at this. That's basically what that looks like. The culprit in this whole thing is this shaft. This shaft here is pushed. These are two shafts basically. This shaft here has the anchor around it, and this is your coil, and this will drive this. If the current increases, it goes into the direction to the left, pushing this plastic plate against the opening here, closing effectively the airflow off. This is coupled, so this is not one piece. And this here, where you can see this is the guide part, which is this brass piece here, which is threaded. And in that thread you have that little end cap, and if you pull the end cap out, then you have this here. So you can screw a M4, I think it is either M4 or M5. You can screw an M4 in there, and you can move this thing in and out. This is about as far out as you can pull it, but you can probably push it in by about 3 millimeters. That's what I tested. It can go in quite some ways. And the reason why I'm looking at this again is this is really important. You can see there's a little flange here and a little flange here. That flange will bump eventually against that housing part here, that outer part here, and that will prohibit this from being pulled all the way out. But you literally can pull this all the way in until it doesn't go any further. So this is basically your adjustment range. You probably have a good 3 to 4 millimeters, and that you can adjust. Then we get to this in a minute to get the exact current for your idle speed you actually want, and I get to that to more detail, but we're still at the issue with these parts being stuck. Now you can see this in this drawing. They have a little bit oversimplified this. Only that lateral part here of that shaft sits actually in the guide when this thing is fully released, so this is fully open in this case. But the reality is this gap is fairly small, and I found a picture of someone who had actually taken this apart. This here is this part here. This is part 89. You can see this. You can see the spring, and this is the shaft, and this is where that plastic, I don't know what you want to call it, that plastic hub is attached to here. You can see this pretty much. This is what that looks like. And here's now the important part. When we look at the shaft, let me get a little bit closer here. You can see that the shaft has a nice shiny color to here. And this is the part which was sitting in that brass tube. And this car was parked for a long time, and the spring had pushed this in the open position, and this started to rust. This is oxidation and dirt, and now what happens is when that current is applied, this is trying to push itself into the brass piece, and that's where it gets stuck. This is the part which gets dirty. And I don't know, I've tried several different ways, brake cleaner, this, that, and the other thing. Is the real issue is, the question is how difficult or how corroded, how much oxidation is on there. And that really will determine everything, whether that valve in itself is still usable or not. If you apply a 5 volt current, a 5 volt DC they operate from 0 to 5 volts, and at 5 volts that I see that valve draws about 1 amp. That's the maximum the control unit will give you. So if you don't put a 12 volt signal on there, they do not operate on 12 volt. You have to go with a 5 volt signal. And then you have to watch this piece here to see, does it go all the way in, meaning does it close all the way off, or does it get stuck? What I mean is this part here, this here will touch this, it will basically close this off here. So this moves out. This takes 1 amp of current, or 0.99 amps, 990 milliamps. And actually that unit reaches that at about 4.3 volts when you measure this out. And then you're gonna see, we can see anything because there's not enough light. Anyway, then this is closed. And the way this basically works is when the RPM runs up, this thing here applies a current and pushes this further down until it is closed, and then the RPM starts to drop off. And as the RPM drops off, the control unit reduces the current and increases this air gap until it finds exactly the position to be at around between 600 to 750 RPM. And now we're coming to the next thing, what I wanted to point out. If you remember, if you watched the other videos, you know that I have 2 units. I have the 004 545 1132, which is the older one, and this is the 006 545 8532. And on these here, they behave different. I have fixed them up. This one brings out a signal from 0 milliamps to 990 milliamps. So do they. This is the control range, just about from 0 to 1 amp. Don't worry too much about the voltage because that is a current control system what they're employing. But the behavior on the way it idles up, it idles, reduces the current down. There's an enrichment process on these big engines which they changed, and they increased the mixture to be much richer. So when you're going up with the RPM, say like you're revving up, you will see and you release the accelerator pedal, the RPM will drop off first around 1000 and then it will drop down. And it can stay at the 1000 for a little while because the EHA valve is enriching the system so your engine doesn't starve out. And they usually reduce this gradually, and that will bring down your RPM. So these 2 units behave differently. It depends on which one you have in here. You will see this one responds differently with the enrichment process, meaning say like whenever you have required the motor to produce power, and that power suddenly is taken off, either by revving up or by driving fast or by driving in general and stopping and then going in neutral or in park, you will see it will run up the RPM on both units, and then it will stay. One stays longer enriched with an enriched mixture than the other one, and then drop off. And there's another part in this which is also important, is say like if you're in that enriched position, and this is why we have the EZL in here, what you can do is the EZL has a vacuum connector which is straight connected to your manifold. And what will happen is they're saying the ignition maps for typical load engine speed ranges and fixed full load ignition characteristics curves are stored in the microcomputer of the EZL unit, this one here. The EZL control unit detects the momentary operating state of the engine from various input signals. Engine speed and crankshaft position are detected by position sensor. The optimal ignition timing for this operating state is determined from the stored ignition maps, taking into account all the input signals. And this is where this whole thing now gets complicated with this whole stuff. As you can see, they have 4 different versions, 2 for the 4.2 liter, the 116 engine, and then 2 different versions for these here. And in general, you can say the older unit, this one here, the 004 545 51132, will work with the 5332. So that computer has this stored in here. And theoretically, the newer version of this, the 5532, ought to work with both of them. But since this thing doesn't know which control unit you got hooked up, it is made, or they made the assumption, the first generation of the EZL works with the first generation of the control unit, second generation with the second generation. If you get them crisscrossed, what will happen is that the enrichment process is also affecting the timing. Your crank angle, basically. And what that will do is this can add 200 RPM to your idle speed. And the way you can check this is by simply, say, like if you're normally idling at 650, 700 and you're winding up idling at 800, 900, when you're going from gear into neutral, for instance, or when you turn the air conditioning, when you're neutral or in a park and you're turning the air conditioning off, if you disconnect the vacuum, what should happen is the unit should start to idle down because you have no more advance. And this is another reason that the EZLs have to work. The vacuum has to work because they're determining between the RPM signal, the water temperature from B11 too, and the vacuum on where they actually are. This is the only 3 signals the EZL actually gets. And what I found out is when you drive at higher temperatures, say like when the ambient temperature is around 90 degrees, 95 degrees, the EHA valve is open after you, for enrichment purposes, when you come from a higher RPM to no load, basically. And then this thing at higher temperatures will kick in and add another 100 to 200 RPM. The way you can test this is by just simply, when it happens, removing the vacuum. And the idle should go back and it should start to then take over here again. This here can override this by advancing the timing. Your timing advances. And that is interesting too, because this will actually enter the limp mode. Say like if this unit fails, the way they fail normally is, unless it gets stuck, is open. And they can increase the RPM, not through this here, but they also can increase the RPM, idle RPM, through the timing. And that is what happens. And when that happens is you can check this by pulling this out. If it runs at 1000, 1100 or higher, then that means that this unit here is not working or the valve is completely stuck. Now, oops, sorry about this, to make this clear. So now we got this part covered. That is this can add 100 to 200, maybe 300 at the very most through timing advances, because that computer has a map in there and it picks out the wrong map, or it thinks it needs to idle higher for whatever reason, and that's how they override the idle speed control valve. So you're normally idling at 650 and then suddenly you're driving for a while and it's hot out there, and then you suddenly wind up idling at 850, 900. And this comes from the EZL. Disconnect the vacuum and it should drop down. If that's the case, then you know it was just the internal computer trying to figure out what profile it needs to use. And this is what they're saying in here. This is what this means here. Detects the momentary operating state. there we go. Operating state input signals. The optimal ignition timing for this operating state is determined from the stored ignition maps, taking into account all the input signals. So they're having like a big memory in there, and they have different scenarios, and they look at the scenario number, where does it match up, and then they determine a advance for this. There's no way you can override it. That's just where this at, and that is more noticeable when these units work, when this is newer than this unit, or vice versa, when they're mixed up. Now let's get back to this here on how to actually adjust this. So the first thing is to combat, or to get this here basically cleaned out. And I guess since you can't reach this part, solvents, I had pretty good luck with the ultrasonic cleaner in this particular instance. This is this membrane they're talking about. This is probably going to be frayed. This thing is not as relevant to the whole thing, because the real problem is here with this thing moving into the shaft. Now, when you release, now we're going back to the adjustment now, to the actual adjustment. So what you want to do is you want to set the screw in here, and if you're idling too high, you want to pull this out. And the best starting point is to pull this all the way out until it is no further moving. Do that carefully, but you have to apply some pull to this, and then put it in and start the car up. And what you do is you hook up an amp meter in the range from 0 to 10 amps. You're gonna measure about 0 to 1 amp, so you could go with a 2 amp range and get a better reading on it. And what I usually do is I take the 2-pin plug off, and I put the black wire straight onto the pin, and then I use one of my 4mm cable and I plug that in. I go to the negative terminal, or positive terminal, and then from the negative terminal I got this backwards here, but it really doesn't make a big difference, with a clip onto the other pin here. So what I do is this one here, I plug this in, and I use a clip, a crocodile clip, going to the negative or positive, and feeding the negative, that yellow one with the 4mm plug in there, in the 2 amp range, and then you can read it. And what you want to do is, you will see this, that the unit, when the RPM goes up, it goes slowly from 0 or 100 milliamps, it goes up 300, 600, 900 milliamps, and then you should hear the engine coming down. Then it's starting to slow down. And then you will see the current is also going to drop, and eventually, when you reach the desired idle speed, somewhere between, on the first generations, they were around 550, 600 RPM. On the later ones, they went up to 700. They added a 100 one. So if I use the newer one here, this idles around 750. And this one here will idle around 600, 650. This is the difference. And what you want to do is, if you're a little bit too low, you have to take the valve back out, push it in, go in about 0.5 millimeter to 1 millimeter increments. That is probably somewhere between 1/64 of an inch to 1/32. You can use a caliper to measure it out. And you would measure this part here, actually, this here. This is basically fully pulled out. So when you start, I put the screw in, and then I tap, I hold it, and then I tap very, very lightly against the screw, unscrew it, and then I measure this. So this is your 0 point. This is as far out as it gets. Then you want to work your way back. Probably I would do it in 0.5 millimeter increments, and then put it back in, let it run, and the engine should be warm at this. So it's a little bit uncomfortable pulling that out with a warm engine. but you want to do this when your water temperature is definitely over 80 degrees Celsius at your normal 80 to 85, 90 in that range. And you basically there, you have this adjusted correctly when your idle speed is at that desired idle speed. Again, the older models gonna be around 600, 550 to 650, with most of them being between 550 and 600. And the newer ones about 700, 750. If you go further out, you can go lower with those, but then the engine runs pretty rough because it has a hard time controlling that. It's trying to get it to 750. So at either one of these two idle speeds, you want to have then a current draw of 800. And you can adjust this. If the current draw is too low, then you push it back in. That will increase the current. If you're like 900 milliamps, then you have to pull it a little bit back out until you get right there in there. And this would be done after you clean this thing up here. And like I said, this is hard to see. You can't really look into this, and you sure cannot see that shaft, unfortunately, the way it sits in there. But this is that gap, and this is what I had in mind. Is when I had the spring released, is at a very high temperature, this got stuck in that brass, and it would keep that valve closed. And then when I tapped on it, then it would open back up, but it would actually push itself out. And when the engine was hot, say like 85 Celsius to 90 degrees Celsius, then this thing got stuck, and the reason is for that dirt. So I cleaned some more stuff, and I put oil in there actually, and then I used compressed air, and I put WD-40 in there on that shaft. Once this is open here, you can basically put the WD-40 or oil in here, and then have the valve move up and down basically. Then you can basically go in here. You can actually see the light shining through now. See, when you go in here, and you can get this up and down. Here we can actually see now the light shining through. This would be to free this up, and this is basically, it's better you clean this up. There is going to be, first of all, dirt on there, and then there's going to be corrosion. And as long as the car's set, especially outside, as worse that issue is. And this is the issue with sitting cars when they're not operating. When this thing operates constantly, this will be in a very nice shape. And the problem starts when they sit. These parts, all of these parts do not like to sit. That is not a part. You're going to have less issues with these things when you run the car every day or every week. So these parts have, movement. And once these cars sit for a year, 2 years, or what have you, this is the kind of issue. The issue is not so much here where that housing basically is on. The real issue is here, the shaft in this brass, which is sort of like a what do you call these, my God, oil light bushings. It's like oil light bushings. If you ever had a rusted oil light bushing, something which runs in an oil light bushing, that would be very similar. And the same cleaning would apply to this, what you would use on a rusted up part or shaft which runs in an oil light bushing. You have this with the Bosch motors for windows, fans, and everything else. They all got oil light bushings in these type of shafts, and they don't like to sit. The same problem you're gonna have is they look like that blackish. And the only thing that I have been successful with doing is using, because you can take them apart, is actually to polish the shaft. First of all, if they're not pivot too bad, with steel wool, and then running them with oil, with a high-grade oil, for several hours continuously in that oil light bushing where they're normally operating. And that is similar what you would have to do here. what you probably could do is to put a 5 volt or 4 volt signal on here, pulsating, say like at 1 hertz frequency. So on, off, or you could a half second. And what will happen is probably if it is stuck really bad, it will not fully close. And then over time, this will eventually free itself up. I would lubricate that with oil. So once this starts, the friction doesn't get too high. And the oil will help then to remove any shavings which are going to come out there. And then probably blow this out with compressed air, with a lot of compressed air. That's how I got the other one going. With grease, oil, and letting it sit for overnight. And then blowing it all out. And it has worked so far. So this is basically what you need to do, is to adjust this to the depth here, or the tension on the spring. So when you're at your idle speed, either at around 600 or the 700 setting, that you're drawing about 800 to 850 milliamps. And then, like I said, is when you have that occurrence that after driving or being in gear, or after the air conditioning has been turned off, you should see it idle up. That is the enrichment process. After a load has been disconnected basically from the engine, it will enrich itself and drive the idle up, and then it should come down. If it stays at 800 to 900, I'm not talking about the 1100 or over 1000. The over 1000 is then the shaft thing. Then if it is just 800 to 900, then you pull the vacuum out, and that should drop it down. If that's the case, then you know that the EZL unit is not fully up with its stored exemplary function responses it is supposed to be having. It has picked the wrong pattern, and that's how you wind up. This is normally not a problem, because when you turn the car off and you start the engine again, it will pick a different pattern and a different advance based on input on the information it gets. It is very limited. Now you have to remember, those units they don't talk to each other. This was the days before CAN bus. Today they talk to each other over CAN bus. And so that knows what module is in there and what the other one has, and when it is replaced, and you have to activate them today too, and this, that, and the other thing. Those didn't have it. So this one here takes, at the best, an educated guess on what this thing does and what the ECU does, or the CIS, the fuel injection system, with the, with your enrichment process of the, I call them the engine control unit. They call it CIS, but it's the same difference as the engine control unit. Enriches, that thing doesn't talk. This has no idea what the oxygen sensor sees or what the ECU sees, and the only thing they're getting is the signal this thing puts out for RPM. So there's no direct data exchange, and it is a hit and miss undertaking here in the control system. I guess if someone had a lot of time, you could probably develop a new control system fairly cost effective, to operate this and the ECU and your fuel pump relay all out of one unit. For $50, $100 unit, can operate the entire management on this car, and you probably would wind up with better results than this, since they're not networked together. So this was a pretty lengthy video, which I figured it would be, but this basically explains everything. And this is what you're trying to shoot for. And again, none of this is going to work unless you have fixed all your vacuum leaks and your timing chain is good, your timing chain tensioner is good, and your timing chain itself is not too far off between the two sprockets, between the two side camshafts, because that can influence that too. You will notice in these units when you clean them is that there is a slight miss in this, which looks like it is having the wrong timing in there. This again is a correlates between the EZL unit, which is taking a guess, to where this thing is, because this is telling this here the RPM and not backwards. So the whole brain in this operation is basically the EZL with no direct data exchange to the actual idle speed control unit. And when these things get a little bit sticky, they tend to vary. You will see this with your current reading. The current reading is not going to be very steady, and you're going to hear it, and it feels like it that the engine is misfiring. But that's not the case. This is this thing here trying to maneuver itself around with this thing depending on the engine load at that moment. And this is not 100% exact science. This was as good as it went with the 80s technology. This is really early 80s to mid 80s technology, what you're looking at. It didn't improve until the late 80s with the introduction of CAN bus, which came, I think, in late 88 by Bosch. Was introduced CAN bus. I think it was 88. And by that time, the system was already in full production. The CAN bus, the 140, the W140 with the V12s and the 5 liters, and their more enhanced management system, car management system, that is already the first generation of CAN bus controlled systems where all systems basically talk to each other. So you have a left-hand side and right-hand side control unit for each side, and they run basically independent and they exchange data. And so that was the next step up. If you're looking for more perfection, or if you're used to the 140s and the newer cars, then this is like a thing going back into the dark ages. So you're going to have some issues there with where it feels like it misfires. It doesn't. It just changes the timing of the advance a little bit. You can see this down here. So I put this for that purpose down here, so you can throw a strobe light on there and you can see where you are with your advances. And they're saying here's the temperature should be below 95 degrees Celsius when you do these tests with vacuum and without vacuum. So you can see with the vacuum it will go higher, and without the vacuum it will drop down. So this is basically a 300 RPM, 150 to 300 RPM difference, depending on how this thing here responds, and the EHA valve on how rich the mixture actually is at this point. This thing does not know how rich the mixture is. It has no clue, and this thing has no idea of what the mixture is. Neither one of these two units have any idea. But yet they're trying to pull this up, and they did this on a guesswork. Basically, that's what they're saying in here. And you can see this. So if you should be within these limits, especially at idle speed. And then, of course, this thing gets confused if you have the newer one in here and you have the older one of these here, and this is idling at 550, 600. Then check with the timing light and see where your idle is, where your timing is on this, and then you can see on how far off it is and how bad of a mismatch it is, or if you close on. And like I said, this is really only relevant, and it is not constant. It is only after the engine was under load. As bigger the load is more prevalent that is. And the increased water temperature, say like when it went up from 85 degrees to 90 degrees or something like this, then it will run on at a slightly higher time delay and ignition timing than when it is cooler, or when it has calmed down the whole system. And then again, the EHA system is extremely slow to respond. It can take 5 seconds to 90 seconds for the EHA valve to adjust the mixture. So if you're coming out of a condition you know, until that actually starts to regulate itself back in or out. That's why this part is so difficult to meet the newer emissions test. You know, if you're trying to come to 0.5% or 1% of CO content, you know, in the exhaust to meet the emissions tests, these units here were more in the 2% range, and they're gonna have a hard time because of this. And they had to do it because that large displacement they have is they have to run pretty rich once you cut off the load for that. Otherwise the engine will die out and will stutter and misfire and that sort of stuff. That is part of this whole thing. Is it's usually why you see this only when you're idling, especially after the engine has been run. Say, like if you're going on a highway and you're driving at a very high speed, you know, and then you come to you exit and you're standing at a stoplight, that would be very noticeable at that point, I'm pretty certain, especially with the age and the, you know, and the mileage on these engines and stuff like this, more noticeable than when the car was new and had 10,000 miles on it. But that's kind of how this plays together. This is the longest video I have made so far. It is probably also the most important one, since it really covers the idle control, idle speed air valve, what they call this, in full depth. And of course it would be nice if you have questions or whatever, you can post them down in the comment section. And I hope that this little PDF is going to help you. Otherwise, I wish you a good evening, and I hope you didn't have too many cold beverages while you were watching this. Otherwise, you may have to watch it again tomorrow when the alcohol effects have, you know, are not as prevalent. With that, you have a good night.